Again, it's a test on this series AK that you're staring at using series BK. Simpler, easier to conclude whether this one converges or diverges. Inequality that we get is sometimes tricky, so they consider if we don't have a definite inequality, maybe we have eventual inequality, something like this. This is AK divided by BK. BK is relatively simpler. Suppose these are approaching L. Okay, so there are various cases. If L exists and L exists and L is greater than 0, then what this says is that, so for example, if L is 2, then what this pretty much says is AK is almost twice of a BK. Not at the beginning, but if you look at the, thousands and millions of times later, the size of KK is almost the size of twice the size of BK if L is 2. Does that kind of make sense? Ratio is almost 2. So this doesn't affect, it's just like constant multiple in popping out. So the convergence of a divergence is equivalent in that case. So it goes like this. If this is the case, if our sample, the simpler one to calculate, if this converges, makes this one converges. If the one that we're testing, comparing with the limit, diverges, and the other one is diverging, diverges. How about that? Because their growth rate is almost like the same, like twice and third times, and we have very nice definite conclusion. If L is a flat 0, then we have a slightly weaker condition. Yes. Right, it happens. If there's like, think about 1 over n and 2 times 1 over n. They're both diverges going to infinity, right? The series is going to infinity. But their rate is just fixed to 1/2. Their behavior is the same. That's what it says. It doesn't say they're actually going to infinity, or all that says they behave exactly like a fixed proportionality. So diverges, diverges, converges, converges. Make sense? Yeah. If L is 0, what does that mean? It's almost approaching 0. That means BK is a lot bigger than AK. Isn't that what it says? If this guy's approaching 0, AK is not matching the size of a BK. BK is a lot bigger, right? So BK can go to, so pretty much from there what we can conclude is AK is smaller than BK. If AK is smaller than BK, which one gives your conclusion? AK is smaller than BK, right? It's used as a convergence. So from there, we have this type of a conclusion. If BK converges, then AK converges. We do not have this inequality, therefore we can't conclude about divergence. If BK diverges, AK is very, very small. It has nothing to do with the BK anymore. If BK converges, AK should be a lot smaller than BK, therefore it forces AK to converges. So we have only one conclusion. The other one is that what if L goes to infinity? L is infinity, that's how they use it, right? What does that mean? AK is a lot bigger than BK, isn't that what it says, right? Ratio is almost infinity. AK is a lot bigger than the BK, right? So AK is greater than BK. Let's go back in here, see. AK is greater than BK. So if BK diverges, it gives you a conclusion that AK diverges. So this one starts like this, BK diverges. AK diverges. This special case is kind of easy to remember. L equals 0 is a good number, not infinity. So go to the convergence conclusion. L equals infinity, it's not very good behavior. So try to conclude diverges. But if you look at the inequality, the meaning of the size of extreme difference of size of an AK and BK, these two make sense in number 1 also. All right? Okay. So let's look at example and think about this one a little bit in terms of strict inequality, but there will be some AN business, large indices and things like that. So it's all, but what I said about this L equals 0 and L equals infinity, does that kind of make sense? L equals 0 makes BK a whole lot bigger than AK, right? That gives you definite inequality result. So here, L equals 0, the eventual inequality would be AK is less than BK. BK is a whole lot bigger, eventually, because it's a limit result. Does that make sense? From there, we easily conclude the convergence. If L is infinity, then this infinity AK is a whole lot bigger than the BK. Eventually, therefore, it pushes the divergence result, right? So I'm going to only explain this first part. It's approaching L non-zero number. So let's see. The proof of the comparison test. Item number 1, the very first one. All right, the idea is this one. L is non-zero, so here's that number line again. Here's a 0, and L is over here, right? I'm going to put L1 here, maybe midpoint in between L and L, so it's half of L. And maybe I can put some number over here, L2, right? So what do we know? AK and BK is never going to L1 and L2 because they're all gathered down to L, correct? These are all positive terms. Limit approaching L, so they're all here. They are never there L1 and L2. For what kind of K? Not at the beginning, but at some point it's going to happen. So they write it like this. For all K greater than some number N, this inequality definitely happens. We don't have exact numbers or anything, but this must happen. Theoretically, it must happen. So there are two inequalities, so we can use anything. That is L1 BK, AK, L2 BK. It's like that. If BK converges, then we're going to use the second inequality. The second inequality says K is going from 1 through infinity. AK is less than K going from 1 through infinity of L1 times BK, right? You can use anything you want to conclude whatever you want. If BK converges, we're going to focus on the second inequality. That L1 is constant, as L1 pops out. This K going from 1 through infinity is wrong, right? This inequality is not true from 1 through infinity. What is the correct index down there? It's n to infinity. It's only true to n to infinity, right? So we have to change that index, lower limit, to capital N. So if you look at just the tail term, this is true. So the right-hand side is K going from n to infinity and BK. If BK converges, why not the tail part converges, right? So this is definitely some number. So it's going to be M1, correct? Because BK converges from n to infinity, still converges. Whatever that number is, I'm going to call that M1. So what does that prove? This one is bounded, right? And this AK is a positive, so it's bounded monotone sequence theorem. It's by bounded monotone sequence theorem, and the series AK converges. Make sense? Next one, what if the situation, we have this inequality. What if the BK diverges? Then we use the second inequality, so the BK pushes up. So if you hit it with the K going from N again to infinity of L1, this was L2 in the earlier inequality. I got this number wrong, so I'm going to change that to M2 and L2 in the above case. L1, BK down there is less than K going from N to infinity of AK. So this left-hand side is L1 times K going from 1 through infinity and BK. And we know this guy going to infinity, right? Because BK diverges. And BK are positive numbers. So this guy is going to infinity, and this k going from 1 through n, ak. Because of that, it pushed to infinity as well. So you can conclude that the series ak, no matter what happened up to capital N, the convergence is determined by what happened afterwards. So this one diverges. Make sense? So bk converges, ak converges. bk diverges, ak diverges. This trap in and here, and down here, makes the convergence behavior exactly the same, ak and bk. Okay? Okay, here's a question.